Today we're going to talk about Chapter 2, the basic concepts of set theory. Set theory was developed in about 1875 by Georg Cantor. They used a number of symbols and different things to represent sets, and we're going to be talking about in these 4 sections of Chapter 2 the symbolism, terminology, how to use Venn diagrams, different options for how to use set theory to solve mathematical problems. So our first section today, we're going to be talking about symbols and terminology. We're going to talk about things like how to designate a set, what is cardinality, infinite and finite sets, equality of sets, and equivalent sets. So the first thing we're going to talk about is what exactly is a set. So a set could be anything that is a collection of objects, such as a collection of dishes, a collection of people in a room could represent a set. People in a club could represent a set. The objects that are in the set are all called elements or members of that set. We have 3 ways of designating or representing our sets. We can represent them with words. For example, the even numbers or the real numbers or the even integers. We could list out the numbers that are in that set, or we have a notation called a set builder notation, which we will look at. For example, for word descriptions, I could say the set of even counting numbers less than 10, and I'm describing that set with words. Or I can list out the numbers that are in that set, 2, 4, 6, 8. Those are all even numbers, they are counting numbers, and they are all less than 10. Or I could have something called set builder notation, and set builder notation is read x such that x is an even counting number less than 10. Let me say that one more time. X such that x is an even counting number less than 10. So it doesn't have to be x, it could be any other variable that you choose, but typically we do use the variable x. Sets are usually given names. Usually they are given capital letters for their names, such as A, B, C, or D. And in this example here, we have a set A that is comprised of the elements 1, 2, 3, and 4. We always use open bracket or curly brackets for sets. Don't use parentheses or square brackets for when you're representing your sets. A set that contains no elements is called the empty set or the null set, and is denoted by either curly brackets that are empty or by the null set notation symbol. To show that an element is a member of the set, we use the symbol that looks like the E. So in this example, for example, we're saying that 2 is an element of the set, 1, 2, 3, 4, but A is not an element of the set 1, 2, 3, 4. We have natural numbers. Natural numbers are counting numbers that you use to count with, 1, 2, 3, 4, 5, 6, 7, 8. Notice that we don't normally start counting from 0. We usually start counting from 1. So those are called natural numbers or counting numbers. Whole numbers include natural numbers plus the number 0. Integers are all whole numbers, and they're opposites or they're negatives. So for example, negative 1, 2, 3, and 4, or positive 1, 2, 3, and 4. Integers do not include decimals, only whole numbers or natural numbers or their negatives. Rational numbers are any number that can be represented as a fraction, p over q, where p and q are both integers, and q cannot be 0 because you cannot divide by 0. They can be written as a terminating decimal, which means it doesn't go on or repeat, such as 0.1 or 0.25. 0.25 can also be represented as the fraction 1/4. Or repeating decimals like 0.333, 0.6666, 0.8888. For example, 0.3333 is a repeating decimal that represents the fraction 1/3. Irrational numbers are the set of x such that x is not expressible as a quotient of integers. In other words, irrational numbers cannot be written as a fraction of p over q, such as rational numbers. A very common irrational number that is used in mathematics is the number pi. There's a pi button on most calculators, and pi is used frequently in geometry problems. Another very common irrational number is the number e. Numbers that do not repeat and don't terminate are also considered irrational numbers. For example, the square root of 2. If you were to put that in your calculator, you would end up with a decimal that does not repeat and it does not terminate. So even though it appears that you have something that could be a fraction, it is not, and it is considered irrational. Real numbers is all of the numbers x such that x can be expressed as a decimal. Basically, real numbers are all numbers, rational, irrational, integers, whole numbers, natural numbers. Any number can be written as a decimal. It might not terminate, it might not repeat, but it can be written as a decimal. So here's an example. Give a complete listing of all of the elements of the set x such that x is a natural number between 3 and 8. So it's very important to pay attention to the wording. Natural numbers means it has to start at 1 and it has to be an integral, in other words, no decimals. And between means that it cannot include the 3 and the 8. So it has to be the numbers between 3 and 8. So numbers that are between 3 and 8 are 4, 5, and 6, and 7. All of those are integrals, and all of those are natural numbers. So that is our solution. Give a complete listing of all the elements of the set of even integers between 4 and 6. So again, integers means there are no decimals allowed. Even numbers are numbers that are divisible by 2. Numbers between 4 and 6 mean they cannot include the 4 and 6. So the only numbers between 4 and 6 that are integers are 5. 5 is not an even number, so this set does not have any elements that match the description. So the solution is the null set. Give a complete listing of all of the elements of the set x such that x is a negative multiple of 6. Multiples mean that I can multiply by 6 and get the number such as 6 times 1, 6 times 2, 6 times 3. Negative means the numbers have to be negative, so I would be multiplying by -1, -2, -3. So negative multiples of 6 would be the numbers -6, -12, -18, -24, and the list continues on infinitely. So you'll notice that we use the ... symbol to represent that it is an infinite set, and we're going to talk about that some more. Give a complete listing of all the elements of the set of all counting numbers greater than 20. So counting numbers mean that there are no decimals. Greater than 20 means that it does not include 20, but it is greater than 20. So this is again an infinite set, 21, 22, 23, 24, and then the ... represents infinity. Cardinality means the number of elements in the set. So if I'm asking you for the cardinal number or the cardinality of the set, we're asking how many elements there are in the set. The symbolic representation of that is n parentheses a, which is read n of a. And n of a represents the cardinality of a set. So if I asked you to find the cardinal number of each of these sets, K has the elements A, L, G, E, B, and R. So K has 6 elements in its set. So the cardinality of K is 6. M only has one element, the number 2. So the cardinality of M is 1. Since the null set is considered to be an empty set, the cardinality of the null set is 0. If the cardinal number of a set of a particular whole number is what we call, If the cardinal number of a set is a particular whole number, we call it finite. In other words, if there are 5 elements in the set, or 6 elements in the set, then we say that it is finite. If I ask you for a set that is so big that you can't list all the numbers, for example, if I say list all of the real numbers, or list all of the even numbers, or all of the odd numbers, that list goes on and on forever, and there's not a cardinal number for the set. So we call that an infinite set. So examples of infinite sets would be the set of all odd counting numbers. So odd numbers are not divisible by 2. Counting means it starts at 1. So 1, 3, 5, 7, 9, 11, 15, 13. And it goes on, and so we have the dot, dot, dot. So it's considered an infinite set. The set builder notation would be x, such that x is an odd counting number. Again, you know, that's a very broad spectrum of numbers, and so that's considered infinite. A finite set would be, for example, the set 1, 2, 3. It has 3 elements. There's no dot, dot, dot in there, so we're only talking about those 3 elements. Another example would be the even integers between 6 and 20. So because I've specified a range of numbers between 6 and 20, then it becomes a finite set. In this case, the cardinality of that set is 6. Sets that are well defined mean that they can easily be, data can easily be put into the set. So for example, the set of even integers is well defined because I know if it's even, it has to be divisible by 2. If it said odd, I would know that it's not divisible by 2. So those are good sets. If I asked you for the set of good students at Germana, that's not a well-defined set because your interpretation of what is a good student and other interpretations of a good student vary. So anytime that there's some impartiality to it, that's not considered to be a well-defined set. Equality of set means that the 2 sets are equal provided 2 conditions are met. And the 2 conditions must be that every element of A is also an element of B. In other words, if set A has the numbers 1, 2, and 3, then set B has to have the numbers 1, 2, and 3 also. And then the reverse of that would be that every element of B is also an element of A. So if we're looking at the set ABCD and the set ACDB, and I'm asking you if those 2 sets are equal, we would say yes, because it does not matter what order the elements are in as long as they have the same elements in each of the sets. If I looked at example B, the numbers 2, 4, and 6 is in the first set, and the second set is the values of x such that x is an even number. So although 2, 4, and 6 are even numbers, the second example includes all even numbers. So that would include 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So since it includes more numbers in the first set, then they are not considered to be equal. 2 sets are equivalent if A and B have the same cardinal number. So that means that they have the same number of elements in the set, but not necessarily the same elements. So for example, if I have the set 1, 2, 3, 4, and another set A, B, D, and C, A, C, D, and B, those 2 sets are equivalent because each of the sets have a cardinal number of 4. But the second example, ABC and ABCD, are not equivalent, even though they have similar elements. The first example has a cardinal number of 3, and the second one has a cardinal number of 4, so they are not equivalent. So I hope this helped you, and let me know if you're having any problems, and plan on doing your homework on My Math Lab for section 2.1 after you've looked at these notes.